fancy version 1, 2, 3.
Exactly.
Okay.
So just like the interval class vector, this represents intervals. These represent index numbers. Remember, the index number is this in the I operation, okay? Now, this is a pentachord, right? This is a five note set. What does this, the fact that I have a 5 here, say? This tells me that under I 0, 1, 2, I should have 5 common tones.
So it'll just map on itself.
So what does that say?
It's
Symmetrical.
Symmetrical, exactly. So remember how in the interval class vector, if you have a number that matches the number of tones in the set, you know it's transpositionally symmetrical. You can use the index vector the same way. The index vector will tell if a set is symmetrical. So let's place now the axis at I2, which then would go through the 1. Sorry, my 1 and 7, and you can see.
Hold on.
There it is.
What did you just do?
I2.
You're going with 5? Okay, so
5
there's
common
5
tones.
common
This
tones.
represents I0. This is I1. This is I2.
Mhm. And you just stuck it on the 1.
Yeah, because I2 goes through the 1 and 7. Remember, you double whatever, wherever the axis comes out of. Okay, so I1 would be here, I2 is here, I3 is here, I4 is here. Okay, remember this?
Nope.
Well, that's, yeah, so, I guess we have to just review and remember that, so,
Let's do it with the normal.
okay,
normal.
let me put it this way, if I put this on the clock face, and I just say, is this symmetrical,
Yeah.
inversely symmetrical, where's the axis?
On the 1
On the
and
1
7.
through the 7, how do you know what I number that is?
Because you
You
double the
double the
1.
line of symmetry.
You double the line of symmetry, or you do 5 plus 9, I mean, we're doing the same thing. 1 plus 1, 5 plus 9, 8 plus 6 plus 8,
They all equal 2.
it's all I2. But the point, you should make the association that I2 puts the axis through the 1 and 7. I5 will put the axis through the 2.5 and 8.5. Okay, you should make those associations as well. So if you say just I8, where's that axis going to go? Where's that mirror going to go? Through the 4 and the 10. Okay? And I wish the other textbook had a list of, maybe it does here. I wish it did. Maybe I'll bring a chart in that has all of the, I mean, it's really, you could create it yourself, but it has all of the axes, all 12, I0 through 12. Okay?
Good.
Uh-huh. Laura?
No, I was just like, can we do the other type of vector for those numbers and like see how they work together, or
Other
do
type
we need
of,
the prime form for the other one?
notice that for index vector, you have to use the normal form, because if I rotate this to some other position on the clock, if I rotate the 01348 to another position, then the axis of symmetry changes. So you use the normal form for this summation square. You can use prime form to determine the interval class vector. Okay. Now let's do another one. Let's do this one. What does this represent? I what? 8. Because there were no 8s here. So I8, remember, you just have the index number. I know that's going to put the axis through the 4 and and 10. We'll do this the other way with math in just a second. But if I now duplicate, create a new set under I8, 5 becomes 3, 6 becomes 2, 9 and 8 become 11 and 0 respectively. And then the 1 becomes the 7. So you see no common tones between the two. Now, if we want to do this with math, let's go back to the I2. So we had 5, 6, 8, 9, and 1. And I want my index number to go down here. 5 plus what equals 2? 9. 5 o'clock, how many hours until 2 o'clock? 6 plus what equals, okay, 8 plus what equals 2? 9 plus what equals 2? And 1 plus what equals 2? And so you see your new set is a duplicate. And if we did the same for I8, we would come up with 11, 0, 2, 3, 7. Okay?
So we just add 5, 6, 8, 9, 1, add it to equal to 8, or add something to equal it to 8 to get the new numbers? That did not make sense to her.
Yeah, so it's
I think that makes
basically
sense.
x plus y equals the index number. Okay.
So that's if you don't wanna use a circle, you just do that.
Yeah, you can do it as with basic math, or you can use the clock face. Either way. Okay? So, yeah, some textbooks, our textbook does not include this, other textbooks do. It's useful primarily just for determining invariant tones under inversion. That's its primary, that's its use, okay? Yeah, the interval class vector, this is the index vector, this is the interval class vector. The interval class vector is a little more useful because it's giving you a picture of the intervallic content of the set. Well, index vector does not, okay? Make sense?
Yeah, and is there anything else that we can get from the interval class vector, just the tritone? You know, is there any more information in the other numbers, or do we just care about the tritone?
This here? Well, we care about everything, so, you know, this tells us, what does this represent? 1, 2, 3, 4 major thirds and minor sixths, okay? This tells us at T4 and T8, I would have 3 tones that are the same from any given 0, 1, 3, 4, 8. So it tells you, again, number of invariant tones. It tells you just how many of each interval is in the set. It tells us that no tritones are there. So if we transpose this set at T6, we'd have no common tones.
Okay.
Okay? And this also tells us that this set, 0, 1, 3, 4, 8, is not transpositionally symmetrical. How do I know that? From this?
Because there's no color.
There's no 5. I have 5 tones in the set. But it tells us that it is inversionally symmetrical. The index vector tells us that. Okay?
So each one of those numbers represents the transposition index number, I guess?
Transposition here. Transposition number. We tend to use the term index number only for inversion,
Okay.
but it's the same concept.
So it'll be like the first one would be T1,
T1 and 11,
okay,
T2 and 10,
okay.
3 and 11, 3 and 9, etc. Because those are representing interval classes.
Because there were 5 common tones, right?
Questions? Other questions?
The 5,
Yeah.
not having a 5 in the vector there tells us that it's not inversional, right?
It's not, no, it tells us it's not transpositionally symmetrical.
What do we mean though, there's not a 5?
It's 2, 1, 2, 3, 2, 0. There's no 5, there's no
Oh.
number
no,
5
None
there.
has a 5 common distance.
Yes.
Okay.
So there is no T level at which you can create the same 5 tones.
Okay.
If it did have a 5, though, it would be transpositional.
Correct.
And inversely symmetrical at the same time.
No, you have to look at index vector for inversional symmetry.
Okay.
This does not tell you inversional
Well,
symmetry.
yeah, but if that had a 5, that would
If
be.
this had a 5, it would tell us
Okay.
inversional symmetry. Yes. And if there's no 5 anywhere here in a pentachord's index vector, it's not inversionally symmetrical. Okay? So we have yet another way of determining inversional symmetry. I don't know how many that is now, but it's a number of ways. Okay. One other, so do you want to do one more? Yeah?
Yeah.
Okay. Okay, what section is?
Could do a nanochord.
How about a hexachord? Sure. Or we could just throw different pitches on the clock face randomly.
2.
Two,
3.
2, 3,
9.
4, 9,
7.
4,
7.
7. And what one? Oh, okay. Sounds good. All right. Let's figure everything out. All right.
Okay.
Great job, guys. You picked one with 2 3s in there, two minor thirds. So we have to go through everything. Maybe you can quickly see, change it? No, quickly see what the prime form is going to be. I don't know. But we need not only prime form, we need the normal form to do the summation square. So let's actually forget about prime form. I think it's going to be this 4 going around. So here's a 3 and here's a 3, right?
Yes.
So you get to where you quickly just imagine 4 around this way, 7 around this way, or 0 around this way, or 9 around this way. 4 to the 9 is a 7. 7, that one's discarded because that's more than 7. 0 to 7, that's
That's more
another
than-
7.
That's 7. I'm talking
Okay.
about the.
And 9 around 2 is another 7.
Yeah. Wow.
We're
Um,
good.
Yeah.
so
We have
4 to 6 is a 4. What was the other? Not this one. 0 around this way, 0 to 4 is a 4. So there's 2 already, that's 4. It's going to be this way for the prime form. 0, 1, 2, 4, 5, 6, 7, 9. 0, 1, 2, 4, 7, 9. Somebody want to double check that that's in the, yeah, this should be it.
Oh, that's a prime. Okay.
Yeah.
Normal order though is
would be 4, 3, 2.
4, 3, 2.
Well, normal order is always clockwise.
Oh.
It's in there, yeah, okay.
So it's 7, 9, 0, 2, 3.
No.
No, it's 0, 2, 3, 4, 7, 9, right?
Is it 0, 2, 3, or is it, so really you have 2 to compare. 0 to 7 or 7 to 3, yes. 0, 2, 3, 4, 7, 9. 0, 2, 3, 4, 7. To be honest, to create the summation square, you don't have to have the proper normal form, as long as the pitches are represented. But it's good practice. Because you'll have the same number of sums, right, in the clockwise, no matter what, yeah.
So
Is that prime form or normal form?
Oh, wait, no, it is actually normal. It looks like prime form, but it actually isn't. We're actually referring to exact pitches. It looks like it, since it starts with 0, but it's, no, it's not
Oh,
prime
it's up there,
form.
I see.
Yeah, prime form. Is that another hand?
I was saying the prime form is up there.
Yeah, prime form is here, normal order is this. It looks like a prime form, but it's actually.
really close.
Yeah.
Yeah.
Easy, first row, because adding 0 to all the numbers. Okay, now, you fill in, 2 plus 2,
Four.
4,
5,
5, 6,
6,
Six,
9,
Oh, wow.
11.
right?
I guess it's too early for me to
5, 6,
It's like
9, 11.
Then
3 plus 3,
6,
6,
7,
7,
10,
10,
12.
12, or 0, 4, 8, 11, 13, 7 is 14, 16,
16 or 4.
and then 9 and 9 is 18, which is a 6.
6.
It's beautiful.
Index vector, how many zeros?
Wow.
2. I had 3. So.
Okay.
Ones,
That's so pretty.
2,
2.
2, okay. Twos, 3,
3,
3s,
2. I think.
okay. 4s,
3,
4.
3. I said 5.
5. I skipped 1.
You got 3 at the top corner, top left corner, 2 at the bottom right. Okay,
5s are
Fives.
2 5s, I think.
1, 2, 5s, okay. 6s,
1,
4.
3, 4.
7s,
3 or 4. Hell.
8s, 1 right in the middle,
And 9.
9,
There's 1.
1.
2.
4 9s,
4.
2 10.
2 10s, and 11s. Okay,
What is that?
did I get that right?
How many sevens?
That's really big.
7s? I had 4 7s, I think. Oh, 1, 2, 3, 4, 5, 6, 7. Yeah, 4. Okay, so what do we know about this set?
It's
It is.
not symmetrical.
It is not inversionally symmetrical. What is that page?
This one shows there's 2 4s, but there's 4. 1, 2, 3. Oh, there's more 4s.
There's 5.
5 4s. Oh, did I forgot to count.
It's easy to consider this as 1,
Yeah.
right? It's really easy to do that, but remember that refers to 0.
So we go to 6, the number 6, or
There's
the
no
6.
6.
No, I'm talking about, since it's a hexachord, we count 6 in,
You're looking for a 6 here, somewhere.
and there's no 6.
There's no 6, so it's not inversionally symmetrical. There's no I operation that duplicates the set. Okay? Let's test something out here. Oh, yeah.
If the 7 was moved to a 6, then it would be, right?
If the 7 was moved to,
If the, on the clock face, if the 7 was a 6.
if the 7 was a 6, yeah, you can see the symmetry there. Yeah,
Mhm.
absolutely. Yes?
Yes.
How come I have 3? Oh no, that's a wrong. Never mind.
Okay, so it also tells me this is a hexachord. I have no zeros. So remember on our chart of hexachords, you have some are self-complementary. This one is not self-complementary because there's no, right? If there's a 0, do you know, remember this on the chart that I handed out? Only some hexachords have different complementary sets. Because some sets, if you take the missing note, some hexachords, you take the missing notes, it's actually another instance of that set. This isn't particularly valuable information, but the fact that I know zeros tells me this one is not self-complementary. Some composers tend to prefer self-complementary sets, so especially when you get into 12th-tone music where the second 6 notes is actually the same hexachord as the first 6 notes. And we'll get into 12th-tone music soon enough. Let's just practice with a couple. Let's take this 1. What does that 1 represent? 1, 2,
8.
9.
1, 2, 9, 8, right?
Oh, the other one's 0, right?
0, yeah. I count from the back. 11, 10, 9, 8. Okay, so where is the axis for I8, it's through the 4 and 10. Okay, so 4 will become itself, 3 becomes 5, 2 becomes 6, 7 becomes, across the dial to 1, 0 becomes 8, and 9 becomes 11. Do the math. Yeah, Jordan.
Could you go over that again? I'm so lost.
Okay, so if I place, what I'm doing is I'm doing this visually at the moment. I know that I8 puts the mirror point, the axis of symmetry, through the 4.
How do I know that?
Because 4 times, you double the 4. And again, I think we need to associate I8 puts the axis through the 4. Now if you think about it, if I put the mirror here, then 3 is going to connect with 5. 4 will connect with itself. And if you do the math, 4 plus 4 is 8. 3 plus 5 is 8, etc. Right? So the way we have been, I think, doing the I operation, determining index numbers, through this basic math. But we're really saying the same thing. Okay? So I'm doing it visually. So if I put a mirror here, 3 at this mirror becomes 5. Okay? And then I'm just working my way kind of this way. Maybe I should. So I took the 7 next and I said, well, at this mirror, I8 mirror, 7 connects with 1. Okay? If we want, we could do the math this way. Once again, 0, 2, 3, 4, 7, 9. And you do the math, 0 plus what equals 8, 2 plus 6, 5, 4, 1, and 11. Place that on your clock face and you'll get the exact same notes, okay? So one common tone is the 4. All right? We will, yeah. Just,
Never mind, I got it.
okay. All right, one other concept is.
Can I,
Yeah.
so basically with that second one, the inversion, you will start the normal form, the prime form on 6 then, right?
With the orange set,
Yeah, so it will be that the normal form starts in 6. That's the 0.
actually, wait. No, it'd be the 4.
The 4 is going the other way. Okay.
And remember, the black set that we started, which direction did we go for the prime form?
That way, yeah.
This way. So if we find an inverted form of the set, then we're going the opposite direction.
Okay.
So, and if you just, if you went through the same process with the orange set, I think you'd see initially, place the 0 at the 4. 0, 1, 2, 3, 4, 7. Okay. Okay, the concept of subsets is pretty simple. So, if I have a tetrachord 0, 2, 3, 6, we could say 0, 2, 6 is a subset. Right? Obviously, you see the 0, 2, and 6 in there.
You can skip numbers to find this outside.
All I'm interested in is, can I find an 0, 2, 6 within this set somehow? Okay? So is that smaller set found in this larger or superset? Okay?
And we only do this with prime form?
Well, there's actually a distinction between, mostly, when we talk about subsets, we're talking about abstract subsets.
Prime form.
So we're thinking abstractly. You can also talk about, I think it's particular subsets, which then you're referring to actual pitches. 3, 4, 7 is a subset of 0, 2, 3, 4, 7, 9 normal form. Yeah. Okay, question. Where is it? Okay. Let's take, 01, 2, 5, 7, prime form. Is 026 a subset?
No.
Maybe O2, but not the
If
six.
you go backwards, is that K?
It is a subset.
Because if you start at 7, you can go both.
Okay, if you think of, so not here, Sophie, what were you saying?
I was saying you go backwards starting at 7?
Okay, so if you put the 0 here and go this
Yeah.
way,
Oh,
6.
it would be 026.
so you have to think conversionally.
So here's, yeah, you have, it's helpful to actually use the clock face. Even though we're dealing with prime form, you can do this a couple of ways. So 01, 2, 5, and 7. If I have those pitches, can I find an 026 in there? Yes, if I do 0 here, 2, 3, 4, 5, 6, okay? Does that make sense? So it's not always just totally obvious at the beginning. The other way you can do this is you take the AIS of the larger set. Here I have 1, 3, 2, and then all the way around is a 5. Imagine the 026, which is a 2, 4, and 6. And you see if you can create a 2, 4, 6 in some direction by combining numbers. So here's a 2, this would be a 4, and then 1 and 5 is a 6. That's another way of thinking about it. But I find that it's easier just to kind of, imagine the notes and then just, just try to figure it out. So here's another one. 0148 is 015 a subset.